All right, so we're going to graph this rational function. We started this a little bit in the last video. We determined that because the degree on top was 1 bigger than the degree on bottom, degree on top was 2, degree on bottom was 1, we were going to have a slant asymptote. And we wrote out the division problem to find the equation of that slant asymptote. It was y equals x plus 8. Okay. All right, so I'll be using that in a little bit. Always, though, the first thing I like to do is get this in factored form and see if it's reduced. Okay. So it looks like I can factor the top, x plus 1 times x plus 2 over x minus 5. No factors in common on the top and bottom, so that is in lowest terms, and there won't be any holes in the graph. Okay. I do like to deal with what's not in the domain, though. 5 would make the denominator 0, so that tells me that we're going to have a vertical asymptote at x equals 5. Okay. I might as well, since I've already found it, go ahead and draw in my slant asymptote at x plus 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then the slope is 1, so we'll come up 1. Whoops, I need to draw it as a dotted line. Up 1 and over 1. And we'll draw that in as a dotted line. Okay. All asymptotes need to be drawn in as dotted lines. The only exception is if one of your axes is an asymptote, then you've already drawn it as a solid line. Okay, excellent. So I've got my asymptotes. Let's get some intercepts. If I look at the y-intercept, its y value will be f of 0. That's just going to be 2 over negative 5. Easiest, I think, to plug in here, because that just kills off all the terms with x's. So that's just negative 2/5. So my y-intercept will be down here, 0, negative 2/5. For our x-intercepts, the numbers that make the numerator 0, well, let's actually write this out. F of x would equal 0. That would mean that x plus 1 equals 0, or x plus 2 equals 0, and x isn't 5, because the bottom can't be 0. Now I know there was nothing that made the top and bottom 0, because they didn't have any factors in common. Again, I like to just remind myself that when I'm working with a fraction, it's not enough for the top to be 0. The bottom has to not be 0. All right, so x would be negative 1, or x would be negative 2. So it looks like I'm going to have an x-intercept at negative 1, negative 1, 0, and at negative 2, 0. Okay, excellent. So we've got our intercepts, we've got our asymptotes. I don't need to check for a horizontal asymptote, because horizontal and slant asymptotes describe the end behavior. If there's a slant asymptote to describe the end behavior, there's no horizontal asymptote. Okay, I get a horizontal asymptote if the degree on bottom is the same or bigger than the degree on top. I get a slant asymptote if the degree on top is 1 bigger than the degree on bottom, and I can't have both. Okay, so I think we've got all the points we need, so it's time to play connect the dots. And it looks like we've just got these 3 dots here to connect, but we've got to respect the behavior of the asymptotes. Okay, so I'm going to mark off my number line so that I can check where things could change sign. Where things could change sign is determined again by the x-intercepts and the vertical asymptote. Because I'm either going to, if I change sign, I'm either going to pass through the axis, which would be at an x-intercept, or jump over it, which would have to be at a place where the function is undefined, which is at a vertical asymptote. The slant asymptote doesn't affect this number line that I'm drawing. I'm just marking off negative 2, negative 1, and 5. Probably mark that that's at 5. Okay, so let's see. I know that to the left of negative 2, do I know anything? I do, actually, because I know that I've got to end up close to this line. And to the left of negative 2, this line is negative. Okay, so I can say just by looking at that, it's going to be negative. Now, if you didn't see that and you plugged in a test number, you'd get a negative value. Totally fine. Okay. All right, between -2 and -1, let's just plug in -3/2 or -1.5. Easiest to do that, I think, in factored form. This would be negative, this would be positive, this would be negative. 2 negatives and 1 positive are going to give me something positive. So between these two x-intercepts, we're going to bump up and be positive. Okay. Between -1 and 5, I can see that we're negative because we've got our y-intercept is in that interval, and we had a negative y value for that. To the right of 5, I can tell we've got to be positive because we've got to end up close to this line, and the y values over here are positive. Okay. All right, so it is time to play Connect the Dots. So I'm going to start out close to this line. I'm going to have to curve over to hit that point, come up and be positive, pass through that point, come down to hit the y-intercept, and then since we're negative, we'll have to be going down as we approach that asymptote. Now, I don't have any points over here, but I know that to the right of 5, I've got to be positive because I've got to end up close to that line. I'm going to actually erase this function because I need some more room here. I've got to also start either really high up or really low down, but if I started low down, I'd have to cross the x-axis to get up here. So we're going to have to start really high up and then curve so that we can end close to that line. So it's going to end up looking something like so. Now, sometimes when students see a graph like this, they say, oh, there's all this empty space here. Did I forget to draw something? The answer is no, you did not forget to draw anything, because to the left of this asymptote, you were drawing this part of the graph. And this is going to go infinitely far to the left. So when you're breaking your graph up into intervals where you're checking for whether it's positive or negative, remember that the slant asymptote does not break things up into pieces. This bit above the slant asymptote goes infinitely far to the left and infinitely far to the right. The part below the slant asymptote goes infinitely far to the left and infinitely far to the right. So the slant asymptote is not relevant in determining the intervals that you're checking for whether your function is positive or negative. There's a lot of empty space here, but if I put something here, I'd fail the vertical line test because I've got points above that up here. So that's my graph. Now I can pretty much see by inspection that this one has no symmetry. I did mention that it is possible to cross a slant asymptote or touch it. The book doesn't actually ask you to check for that, and I generally won't either. While it is possible, if to cross it you'd have to then change direction and come back and sort of introduce a bunch of curves, that's unlikely behavior as long as you've got relatively small degrees on the top and the bottom of your fraction. Once you get to calculus, you'll actually have some additional techniques for determining how often the curve changes direction, so it becomes a little bit easier to see. But generally speaking, when you're playing connect the dots, draw the simplest curve that you can that connects the dots and respects the sign of the function and the asymptotes. All right, I'm going to have you folks try one. And again, because these are time-consuming problems, I want you to get a jump start of the homework by working through these video problems so that you don't say, oh, do I do this problem or do I do the homework? You can do both. Okay, so this is problem number 83 from the homework. The function is x squared plus 7x plus 10 over x plus 3. I don't remember what the book calls that. I will check. What did I say this was? 83. Oh, it's f of x. Excellent. Not that the name matters. The formula is what matters. But go ahead and graph that, and then we'll go over that together in the next video.